So for Gauss's law, what I'm going to do is this, not this again. I'm going to go ahead and share the screen. All right. Let me make sure this one works. Give me a second. Okay, that works. And before I get to that, I want to get to this. Y'all should have this. I sent it to you earlier. Are you with me, class? I actually have a PowerPoint version right here of this. Well, I'll just get to the, I'll try to cut to the chase. This is just a bit of history. The guy, there's two people, really three, that had a great deal to do with electromagnetics and the development of the theory. The first was actually not Michael Faraday, but he's given a lot of credit because he put the magnetic and electric field equations together to develop the wave equation. But this is the famous Scottish physicist, and he's the guy that's credited with really discovering several things. Y'all have heard of Faraday, right? Michael Faraday, the law of induction. Now, Maxwell's the guy that's really the person that we look at as the one who actually derived the wave equation and came up with it. He solved this and came up literally with equations that defined what the speed of light would be. And then the Michelson-Morley experiment effectively measured it and proved there was no ether. You don't have to know much about this guy, just know how to use his laws. So here's Faraday's law in a nutshell. What he says is there's something called electric flux, and it's caused by charge. Now, y'all know charges in coulombs. This is the units we select. So what happens is that if you put a charge inside any kind of closed surface, there's something called the electric flux density that will be penetrating that surface. And if you think about it, what it really is the charge divided by the surface area here. Now, this will become a little more clear in a second. If you just take a look at this problem, if that's a spherical problem, if I have a charge plus Q on the inside, it will develop a minus Q on the outside if that's a conductor. But the amount of flux that's flowing there will be Q over the surface area, which would be 4 pi r squared. Do y'all know the surface area of a sphere is 4 pi r squared? This is in a nutshell. I'm just giving you the big picture. And you don't have to know that well, but you'll have to use the law. So what does Faraday's law say? Really, what it says is that the electric flux density is related to the E field. This is what you take of it. In free spaces, D is equal to epsilon naught E. You all remember that from physics class? This is a basic relationship between the flux density D and the electric field E. Now, something I have to tell you, we've been talking about the electric field from the Biot-Savart standpoint, right? We've assumed a charge, and then we've defined the field from that charge as Q over 4 pi epsilon naught r squared AR. That really came from Faraday's laws, but it's called Coulomb's law, and there's a lot I could say about this. The constant epsilon naught is experimentally determined, and it's really 8.854 times 10 to the minus 12 farads per meter, or a lot of times it's written as 1 over 36 pi times 10 to the minus 9 farads per meter. And I'll spend more time on that in a bit. I don't like using PowerPoints, but for the sake of perspective, it helps, all right? I'm going to go through this fairly. Can you all see this, class? What I've got here? All right, now, there's a lot of things that he's going to have here that seem a little foreign. This symbol psi, the thing that looks like a pitchfork, that's called the amount of flux, and the units of that are in coulombs. Now, D, the magnet or the electric flux right here, D is actually in coulombs per meter squared. Some of this I'll talk about later. The thing to take about it is the total flux going through any surface is right here, is the integral of D dot ds. I'm going to do examples. I'm going to put a lot more meat on this, but I'm just trying to present this in a way that at least you understand when we're talking about flux, we're talking about something that is proportional to the E field, and you have a feel for the E field. And it really has to do with the amount of, if you integrate over the total surface area, it's the charge inside that surface. All right, this is Gauss's law, and this is the one we're going to be using today. Gauss really said the integral of D, one of the things he's noted. By the way, are you familiar with Gauss, most of you? He's extremely famous, right? He was a mathematician, he was brilliant. I don't know, I've told, if you've had me before, you know this story, but when Gauss was, I think it's second or third grade, the people used to give the students something to do to keep them busy. So they asked him to add up all the numbers from 0 to 100, and that takes a good 20 minutes or so. So the teacher could grade or something like that. Well, Gauss, being Gauss, would have none of that. What he did is write all the numbers, 0, 1, 2, 3, 4, all the way to 100. And then below it, he took them and wrote them backwards, 100, 99, 98, and so forth. Well, he added the columns, and he said each column added up to 100. And he had 101 100s. So he multiplied 100 by 101. When that was twice the actual sum, then he divided by 2, came up to the teacher. This is a well-known story. In about 2 or 3 minutes, gave her the answer. Teacher flipped, didn't know what was going on, introduced Gauss to some college professors, and from then his career took off. That's a true story. You got to read about it. The guy he's one of these natural savants, and these are the kind of people that really did. Newton, Gauss, people like that, they were the real underpinnings of modern physics and mathematics. So that's for your information. I'm going to apply Gauss's law in a second my way, but I'll tell you one thing that is important to understand. We use Gauss's law only in highly symmetric situations where we have either spherical or cylindrical or planar symmetry. And now I'm going to jump to my dot cam if I can. Because really the rest of this, until you, actually I can do this here, right here. Remember, Gauss's law says the integral of D dot ds is the charge inside. Does everybody understand that? Can you all hear me? So the integral of D, the electric flux over any region right here, is the charge inside. When we talk about D over a surface, integrated over a surface, we're going to be talking about D integrated over either a spherical, a cylindrical, or a planar surface. Does everybody understand that? We're not going to be talking about proloid, ellipsoid, or just random surfaces because it wouldn't help us solve the problem. We're trying to find the D field from different charge configurations because if we find the D field, we have the E field. Now bear with me. This is the key. Integral of D dot ds is equal to the charge enclosed. Here he's showing what the integral of D dot ds is in spherical coordinates. I'll spend more time on that later. So just for a second, try to follow me on this. Let's say we just have a point charge, Q. And we move out a radial distance r from that point charge. And then we create a spherical surface of radius r. You can all imagine that, right? Now, Gauss's law says that the integral of D dot ds is equal to the charge enclosed. If it's a point charge, we know the charge enclosed is Q, right? Are you with me? Now, D dot ds, D points radially away from the charge that's causing it. The integral of D dot ds is really going to be D of r that's at a given radial distance is the same. And that's where he has this. He has D of r AR. dotted with r squared. This right here, r squared sine theta d theta d phi, is a differential surface. Remember we talked about differential surfaces? Y'all remember that? Where we're trying to talk them with spherical and Cartesian, or in cylindrical coordinates. Y'all, everybody knows that, right? We talked about that. So here, this differential surface is on the outer edge of the sphere. It would be the little chunk of the sphere. So it's r squared sine theta d phi in the AR direction. Now, I didn't get to this yet, but y'all had dot products, right? If you had ax dot ax, what is its value? Anyone? 1, right? Ax dot ax is 1, correct? If they're Cartesian. What is ax dot ay, anybody?
0.
0. What is ax dot az?
0.
Everybody follow me? So a dot product, a vector, a unit vector dotted into itself is 1, dotted into any other orthogonal part of the orthogonal coordinate system is 0. AR dotted into, for instance, if you put in d, call it d phi, a phi here, well, when you dot, if you wrote the entire d field down, you would have a d in the phi direction, a phi, and a d in the theta direction, a theta. But when you dot that into AR, it goes away. So the only thing I care about is dr, AR. This is what this dot product comes down to. We can take dr and r squared outside that integration. Now we're integrating sine theta d phi, and that's over the complete surface. Now, this is not shown here, but when we're dealing with spherical coordinates, you have to integrate d phi from 0 to 2 pi. Are you with me on that? And we have to integrate d theta from the north pole, or 0 to the south pole, or pi, or 180 degrees. With me? So when you do this, if you integrate d phi, you get phi from 0 to 2 pi is just 2 pi. And when you integrate sine theta d theta, you get minus cosine theta, right? And then you evaluate it from, you evaluate it from 0 to pi, and you get 2 out of it. So it's going to be 2 times 2 pi, or 4 pi. And that's what he does here. He just says this entire integration here would come down to 4 pi r squared dr. Follow me? And that's just the surface area of a sphere. How many know that the surface area of a sphere is 4 pi r squared? Okay, you got to know that by heart. How many know the volume of a sphere is 4/3 pi r cubed? Right? Those are things you have to know, like 1 and 1 is 2. You got to be that, it's that obvious to you. So when we have a point charge, we're at a distance r away from it. When we integrate d dot ds, we simply get the surface area of 4 pi r squared times d of r. At a given radial distance, d will be the constant. It will not change in value. Is equal to q, and therefore dr is q over 4 pi r squared. And furthermore, if it's in free space or in a vacuum, if we take d, remember d was equal to epsilon e. If we wanted e, we simply take d divided by epsilon here. Now that, I didn't want to waste time writing it here, but that is a simple application of Gauss's law to a point charge. How many understand that? Okay, you guys getting it? John, do you see this? All right. I'm trying to read you guys because if there's something unclear, I need to address it. I'm being casual about this because you've seen this before in physics. I know that. You couldn't be here if you hadn't had that in physics. Now, the next part is an application of Gauss's charge, or Gauss's law, to a line charge. So we've done this problem with Coulomb's law, right? We took the differential electric field from a differential chunk of charge at the given radial distance, and we integrated that from minus infinity to infinity, and we found out that it was going to be rho L over 2 pi epsilon naught rho A rho. You just did a problem like that, didn't you, class? All right, here's how you get it with very little work. First, if you have an infinite line charge and I come out a distance away, A or R really, or call it rho, well, you all agree that anywhere around that surface, if I look at the wire, it looks the same. Do you all agree with me? Now, this is something about symmetry I try to tell people. If you want to know if something is spherically symmetric or cylindrically symmetric or planar symmetric, take that something, if it's this book and I look at it at different aspect angles, even if I set the distance from the center of that book constant, it looks different. So This thing has no cylindrical or spherical symmetry. I can't use Gauss's law effectively here. You use Gauss's law, I mean, you use Gauss's law to really find the D field when there's a highly symmetric situation. But this one is, if I have an infinite line charge, you all see that if I go out a distance A in this case from there, that line looks the same no matter what aspect angle phi I'm at. Everybody agree, right? Now, so if I integrate D around, by the way, which intuitive sense tells you this, but you realize the D field from this can only be radially outward because it's an infinite line. But even if you don't, it's only radially away. Now look at this. If I take a look at the integral of D dot ds, the first thing I have to make sure you understand is the D field has only a radial component, a rho. It's only pointing away from the center of the line. Does everybody give me that? It can't have any other component. And I don't have a real good mathematical argument for this. Some of it I'll say is intuition, but you know, no matter where you are in this line, if you take the differential charge, the E field from that has to be radially away. And it will have a vertical or horizontal component, but it's radially away. It's got some component radially away. You agree with me? All right. So if we take the integral of D dot ds, it would be the D field's in the radial direction. If I take the surface, let me try to do this. If I look here on this surface, the differential surface, now we've talked about this, that the differential surface on the outer part of that can, this curvature right here, would be rho d phi dz in the a rho direction. Do you all agree with that? I'll say it again slower. It would be rho d phi, that would be the azimuthal or the wiper arm, then dz, the vertical, that would be an area, and that area would have vector sense in the a rho direction. Do you all agree with that? And we would say the integral of the D field, well, the D field's only in the radial direction. It's right here. It's just D rho of rho, a rho. When I dot that in with that differential surface, I simply get D rho of rho times rho d phi dz. And I'm going to go to the next page. And that's what he's doing right here, right? I hope this doesn't bother you too much that I'm using this, but it helps so we can do problems after we're done. So when we look at the actual, he starts with the top part of the can. Do you all agree that on the top here, the differential surface would be rho d phi az? Take a look at it, right? It would be rho d phi is the wiper arm like this, and then I'm sorry, the top, it would be rho d phi would be the wiper arm, and then d rho would be the radial outward. Do you all see that, class? This is the differential surface at the top of the can or the bottom. Well, this would be at the bottom. Can you all see that? Ben, can you see this? You look like you're squinting. Everybody?
Yeah, I can see it.
All right, remember, you're always talking about the differential distances. So if you're going d phi, it would be rho d phi would be the arc length, and then the radial direction would be d rho, and it has to be in the az direction, it has to be perpendicular. So that's this top part right here. And you'll notice when you take this and dot it into the vector a rho, D, well, D is only in the a rho direction, so it's 0. And it's the same with the bottom of the can. Do you all see that? If we integrate it over the total surface, we'd have to integrate over the top and bottom and the outer surface right there. Correct, class? All right. And then finally, this is the differential I mentioned. This is the one that counts. So he says a rho dot az is 0. Finally, coming down here, we can say the integral of d dot ds would be equal to just d rho a rho dot rho d phi dz a rho. And then you can see the integration of phi goes from 0 to 2 pi. It's all the way around the xy plane. And dz goes from 0 to h, and you would have 2 pi h. Sorry about this. 2 pi h rho times d rho. Does everybody agree with that integration? How many remember this from physics doing this stuff? You did this in physics, didn't you? When you had, whoever you had made you use Gauss's law. Didn't he? Am I wrong? You should have done this one. This is a classic. All right. Next, what is that equal to? That's the total charge enclosed. Well, the total charge enclosed is rho LH, right? You all see it right here? Right? And so if I equate this to this, you'll notice that the h cancels, and I get d rho is equal to 1 over 2 pi rho. And that's right here, right? You agree with me? It's rho L over 2 pi rho. Now that's the D field. How do I get the E field from that, anyone? Anyone?
Divide by epsilon naught.
That's it. Divide by epsilon naught, and that's all it takes. And you got it. And you see, we didn't do a single integration. Remember how those integrations get hairy? Someone, when you're integrating, you got like a rho over square root of rho squared plus z squared to the 3/2 power, and they get annoying. This is simple. Now, it does assume it's infinitely long. You have to be aware of that. All right, I'm going to keep going. I'm going to do problems. What I'm doing, we didn't do a spherical one. How about if I do one in spherical coordinates for you, and I'll give you a real problem, and using Gauss's law. So I'm going to go to my document camera. Now, this document camera some days, it's no good. Hang on for 1 second. If I don't elevate myself a little, I can't do these things very well because it gets crunched down. So now what I'm going to do is this. I'm going to do a problem using Gauss's law in spherical coordinates. Please follow me on this. First, I define the problem. I'm going to have a spherically symmetric charge distribution. So I'm going to have this. That's X, Y, Z. We just put those in there for reference. And we're coming out at distance R. And I'm going to say for R greater than or equal to 0, less than or equal to A, I'm going to have a charge density, a volume charge density, rho V is going to be equal to rho and just K times, not rho, sorry, make it R times K and put it as coulombs per meter cubed. Let me write that a little better. Rho V is equal to K times R, and this is for 0 greater than R, less than A. And then I'm going to say that rho V is equal to 0 for R greater than A. So really what you have is some sphere right here, and there's charge density inside the radial vector, inside the distance A, and outside the charge density is 0. Everybody see that? So it's a ball. Now we're going to apply Gauss's law, and we're going to get the D field inside and outside. Are you with me? Everybody? So when I do that, first I say for the region R less than A greater than 0 or equal to 0. I write Gauss's law down, and I say, Gauss's law says the integral of d dot ds is equal to really the charge inside, right? Well, what is the charge inside? Well, it would be the integral of rho v dv. It would be a volumetric integral, right? We're trying to find how much charge is inside a volume. Now you can see the pieces of the puzzle coming together. So how far out do I go? Well, I'm going to say I'm going to go out first to a distance r and just put a surface around there. So I'm trying to find the D field on that surface at a distance r from the origin. That's a messy drawing, but I think you get the idea that what I'm really doing is this. I'm saying that there's a spherical surface that's inside A, and I'm coming out at a distance r, and I want to find dr. That's what I'm after. You got me on this, class? And you all see that's spherically symmetric, right? If the charge density is just a function of r, then it doesn't matter what theta and phi are. Now, given that, the integral of d dot ds, I'll do it one time, and you'll never have to do this again. The integral of d dot ds for spherical coordinates is equal to the integral of dr ar dot r squared sine of theta d theta d phi, it's a double integral, dr, and it's in the AR direction, by the way. So that's just that's the D field. This is the differential surface in spherical coordinates, right? I'm going to do the dot product. Theta goes from where to where, guys? Anyone? Just so I know you're listening. Theta. Anybody?
0 to pi.
Right. And what about phi?
0 to 2 pi.
Right. Now this will always be true for if you're using Gauss's law in a spherical system. Now AR dot AR is 1 just as before, right? So when I take a look at this, this will be equal to R squared comes out in front, and then you'll have 4 pi, right? And then D of R. Now this is just the surface area of a sphere, 4 pi R squared. And by the way, we did this integral a second ago. That's why I didn't spend any time on it. But when I integrate d phi, I get phi from 0 to 2 pi is 2 pi. When I integrate sine theta d theta, I get minus cosine theta evaluated from 0 to pi is 2, right? Minus cosine of pi, well, cosine of pi is -1, so minus and minus is 1. And then it's minus, and it would be minus cosine of 0, and that would end up being 1, 2, and it's 1 plus 1 is 2. So it's 4 pi times d of r. Agreed, class? But we have to find the amount of charge inside that region, right? Also, because remember, the integral of d dot ds over a closed surface is really the charge enclosed. I call it q inside the surface. And that's really the integral of rho v dv inside that surface. Can you all see this okay? Remember, that's the charge inside a spherical surface. It's how much charge is inside it. Now we have to do rho dv. So this is the next part. So the integral of rho dv, this is spherical now. First, I put the integral, I put what rho is, and I arbitrarily defined rho, the volume charge density, rho v, as k times r. So I put down k times r, and I know the units are coulombs per meter squared, so when I do this integral, the units will be coulombs. I'm not going to mess around with any times 10 to the minus 9th business. Now it has to be times the differential volume in spherical coordinates. And what's the differential volume in spherical coordinates, people? You're going to have this available to you, but if you work enough problems, it'll be second nature. Well, what is it going to be? It's going to be the outer surface area times the differential dr, wouldn't it? Remember? So the outer surface area was simply r squared sine of theta, d theta, d phi, but then it would also be times dr, and that's the differential surface area, differential volume in spherical coordinates. I'll call it VOL. Can you all see that? Everybody? Now, I have to put the limits down. The first limit is it's theta. Where does theta go from? Anyone?
0 to pi.
Right, and I ask you these things to try to get a little participation. It'll help you retain it. The next is phi. Somebody besides Tyler, where does it go from? Phi. Fowler, where does it go from?
0 to 2 pi.
Thank you. And now this is the one people get wrong. Where does R go from? Ben, how about you? I'll pick on everybody today. But
Is it 0 to A?
it's 0 to R, not A. You're inside A, right? We're only going to R. We're between 0 and A, right?
Okay.
I'm so glad you said that. You got to make sure you don't put down. Here we're going from 0 to R. Our surface is somewhere inside. It's between 0 and A, right? It's not A. Got me? It could be, but it's the surface we're saying at an arbitrary distance away from the center, yet inside the distance A, we're putting a surface. That's where we're evaluating D. Can everybody see that? Got it, guys? All right. Now, what happens to this integration? Let me take it down here. When I take a look at this, This is the differential volume. I have R squared times R, right? I'm going to do the outer one first. You see, I have R times R squared times R. That's R cubed, correct? And I integrate dr. What do I get? R cubed dr integrated is R to the 4th over 4, correct, class? Right? So I have R to the 4th over 4 evaluated from 0 to R is just R to the 4th over 4. That's the first integration. I mean, that's the outer integration. Now the next integration is d phi. Nothing inside here is a function of phi, is it? No. When we integrate d phi, we just get phi, correct? And we evaluate it from 0 to 2 pi, or we multiply this by 2 pi. Agree, class? Now we do the integration of sine theta d theta. And that is minus cosine theta, right? Minus cosine theta evaluated at pi is what?
1.
Minus 1, right? So we have minus 1, right? And then it's minus a minus cosine of 0. Cosine of 0 is 1, so it's 1 plus 1 is 2. That's the only point I'm making. And this whole thing comes down to what? Just pi times r to the 4th. And it would be in coulombs, and that would be the charge inside the region. You could call it Q as a function of r. That's how much charge there is at a given radial distance r inside that region. Does everybody follow me on that, class? I'm using Q to indicate total charge inside, okay? How many are with me here? I'm trying
And
to,
did you have a K value inside of that?
yeah, I did. And that K value mysteriously lost itself. You're right. I put that there as an arbitrary constant. Everybody okay with that? Now, that charge is equal to the integral of d dot ds, and that's right here. So now I say that 4 pi r squared dr, that's this, that's the integral of d dot ds, is equal to the charge inside is equal to k pi r to the 4th. And you can see it's pretty obvious what happens next. I can say that d of r, right, will be equal to k, the pi's cancel, right? Now I have r squared here, r to the 4th, so it would be r squared, and it would be divided by 4. Do you all agree with me? And that is true for r greater than 0, greater than or equal to, and less than or equal to a. So we've got that. Now the next part is what happens if we're outside where the charge, where there is no added charge density. So I'm going to flip the page, okay? Now, when you take a look and you're outside, this would be for r greater than a. The integral of d dot ds is still equal to the charge inside, q inside. Now, we just did this integral, right? Y'all remember what it is always for a spherical system? It's the surface area of a sphere, or what's the surface area of a sphere? Caleb, I'll get you into the conversation. Can you all hear me?
Yeah.
Go ahead, Caleb. You got to unmute yourself.
Can you hear me?
Yeah, go ahead.
It's 4 pi r squared.
Yeah, just making sure. And it would be times dr. So this is 4 pi r squared, right, times dr. And that's equal to the charge inside. Now, we're at a distance greater than r. So basically, we've got all the charge will be inside there. Follow me? With me? If you're greater than a, the charge density only exists up to a, and it's 0 after that, right? So now I go ahead and I say, well, it's going to be the integral from 0 to a, the integral from 0 to 2 pi, and the integral from 0 to pi. And here, you're going to have the charge density, which is k times r, right? I'm rewriting this, but I'll get to the gist of it. And then it's going to be times r squared, and then sine theta, and then it's d theta, d phi, dr. Y'all with me? I just restated. But now we go not to r, but to a, because now it's all the charge. Remember, past a, there is no charge density for r greater than that. With me, class? All right, what is this going to become? Well, on this side, when we integrate r cubed dr, we get r to the fourth over 4, right? I got an r here and an r squared here. That's r cubed. Dr is r to the fourth over 4. I'll put the k in first. So that, and when we evaluate it from 0 to a, we get a to the fourth over 4. That's the first one. The second one, when we integrate d phi, we get phi. Evaluated from 0 to 2 pi is just 2 pi. And the last one, when we integrate sine theta to d theta, we get minus cosine theta. Evaluated from 0 to pi is simply going to be equal to 2. Are you with me? That's equal to all this stuff, and that's equal to 4 pi r squared d of r. And pretty much you guys can see this. That's a 2, by the way. The 4 pi is canceled. You all see that? Everybody? 4 pi's cancel. Then I take r squared over here. And now I have d of r. And that's true. That's what it is. That's d of r. I've got a point to make. Once you guys get done writing this, it's important. Now, with Gauss's law, something interesting happens. Once you are outside the region where the charge density exists, all the charge density has to be inside. Then as you move away from that, the D field will always fall off as 1 over r squared. You see how it's falling off as 1 over r squared? If it is a spherically symmetric problem. Are you with me? It looks like a point charge. And you'll find for a cylindrical, any kind of cylindrical system, once you move outside where the charge exists, then the D field will fall off as 1 over rho. All right, because remember, D field from just a line charge is rho L over 2 pi epsilon, or the E field, rho L over 2 pi epsilon naught rho, right? Keep this in mind. These are important things to catch. So that's spherical. And we can keep adding more and more complexity. I could say I have an inner region of charge, right, from 0 to A, some charge density. Then I could have a void where there's no charge from, say, A to B. And then from B to C, I could have another charge density, right? And you would always have to find the total charge inside the region and equate it to the D field integrated over the surface. Now, the nice thing is the D field integrated over the surface in for spherically symmetric cases will always be just 4 pi r squared times D of r. That's the nice thing. You never have to do that integration again. On the other side, you may have to do some integrations, okay? How many understand that right there? The principle, at least, of Gauss's law. It's always the integral of d dot ds is charge inside. Now let's do one for a line, or for a cylinder of charge. So now I'm going to do this. I'm going to take a cylinder. Assume this is the z-axis. And I'm going to take a cylinder here. And call this radius A. And here I'm going to define the problem. I'm going to say between rho is 0 and rho is the radial coordinate, which would be here. That's rho. Between 0 and A, there's a volume charge density. And I'll say rho V here would be equal to, and I'm making one up, I'm going to say it's equal to rho times K, coulombs per meter cubed. Right? So I'm using a constant K. Rho is just the radial distance. Can everybody see what I'm doing here?
Can you scoot it up just a little bit, please?
Yep. Yep. But it's just what I'm doing is basically the same charge density as before, only instead of rho we have instead of r we have rho. Okay. You got me on this? It's arbitrary. It's a function of rho, in other words. So When we do this, and we apply Gauss's law, the goal is to find the D field at any point. When I say I want the integral of d dot ds over the surface, and I say that's the charge inside the surface, right? Well, when I do the integral of d dot ds, try to understand this. The outside surface here has ds equal to simply, it would be equal to rho d phi dz, and it would be in the a rho direction. Does everybody see that? That would be the outer surface of my can. The upper surface we just talked about, right? The upper surface would have a differential surface equal to rho d phi. That would be the wiper arm moving this way. And then it would be times d rho. That would be going out radially. And it would be in the AZ direction. Now we talked about that. Correct, class? And we know that the D field, because of the symmetry of the situation, it's cylindrically symmetric, right? Whenever you have a cylindrically symmetric system, the D field must point radially away. It has to point in the direction of the symmetric, what we call the degree of symmetry. Like in spherical coordinates, it points out radially because it's spherically symmetric. Cylindrically symmetric, it points out radially as well, only the identifier is rho, it's not r, okay? Y'all see that? Now, when we have the integral of d dot ds, because the D field here, and we just talked about, the D field is only going to have, it'll only be in the rho direction. It'll be a function of rho, and it'll be in the a rho direction. There is no z, there is no theta component. Therefore, when we do the integration of d dot ds, the top and the bottom of the surface, here and here, will have no contributions. Can you all understand that? Let me get your hands, show of hands that you do understand. It's because az dot a rho is going to be 0. And so I don't even write that down. What I do here, he likes to put a height in, and I'm going to give you a tip. Whenever you're making something and you get to choose the height of something or the length of something, make it equal to 1. You know why? Because that way you can never forget to divide it out. 1 divided by itself is 1. If you just leave it in there, 1 is 1 is 1. You don't have to worry about it. So now if I let that height be 1, I can say that the integral of d dot ds, right, over the surface is actually the integral, and it's a double integral, of d, which is d of rho a rho, dotted in with ds, which would be rho d phi dz. Here, dz would go from 0 to 1, which is nice, right? And this would be a rho, by the way, the surface. And here, phi would go from 0 to 2 pi. Y'all agree with that? It's not the greatest handwriting, but I hope you get my point. That's the D field. It's in the rho direction. This is the differential surface of the outer area. A rho dot a rho is 1, right? Now, when we integrate d phi, we get phi from 0 to 2 pi is 2 pi. When we integrate z, or dz, we get z from 0 to 1 is just 1. So now that means that this side of the integration is just going to be equal to 2 pi rho d rho. And I want to tell you, that will always be true for cylindrically symmetric problems. Got me on that, guys? Now that's equal to the charge enclosed. Well, how much charge is enclosed? First, I have to note this. I'm between 0 and A. So if you want to, and this is going to look a little messy, but if you come out a distance rho away and just draw a cylinder within there, right? Still going to have the same height, but y'all follow me? I'm inside the cylinder. I'm not at A. I'm between 0 and A. Understand? And we're going to go ahead and apply Gauss's law. So this would be the Q inside. And then I say that Q inside will be equal to, and now it's a volumetric integral. It's a triple integral of rho. Sorry, it went out of focus. Come on. Of rho. Well, my rho is K times rho. And it's times the differential volume in cylindrical coordinates. How many know what the differential volume is in cylindrical coordinates? Just take the differential lengths on the axis. It's going to be what? Rho d phi, right? Then it's going to be d rho dz. Agreed? Y'all with me? Now, the phi integration is the first one. That will go from 0 to 2 pi. The rho integration is the next one. Where will that go from? Fowler, you want to do this one again?
The d rho would go from 0 to 1.
Rho would go from 0 to rho, right? I should actually prime that. What I'm trying to say is we're not at 1, we're not at A. Rho is this thing, right?
Oh, yeah.
It goes from 0 to rho. When I'm going to drive that point home one way or the other, but I'm trying to not have you make the common mistake of saying from 0 to A. That's common. It doesn't. It's between 0 and A. It goes to rho. From 0 to rho. Technically, I should prime this. You know, I hate doing that. You know what I'm talking about. You can't integrate dx, right, if you have a limit of x. So this, we make this a prime variable. It's called a dummy variable that goes away when we do the integration. Finally, dz goes from where? Now Tyler, or Fowler, you can answer.
For dz?
dz would go from where to where? From
0 to 1.
Thank you. You agree with me? You'll notice we don't even need that dz integration, because when I integrate dz, I get z evaluated from 0 to 1 is 1, isn't it? So get rid of that. Now, what about the next integration? When I integrate rho, it's actually rho prime, but rho squared d rho, what do I get? Rho cubed over 3. Thank you. Rho cubed over 3. And that is evaluated from 0 to rho, so it would be rho cubed over 3. I'll put the k out in front too. Then I integrate d phi, and I get phi from 0 to 2 pi is 2 pi, isn't it?
Yes.
That's the charge inside. We set that equal to the integral of d dot ds, and the integral of d dot ds is here, right? So we put 2 pi rho d rho here is equal to this. Okay, everybody? I know I'm a bit over, just hang with me. I want to finish these thoughts. Now, y'all see the 2 pi cancels.
You skip the
Yeah.
paper.
Thank you. The 2 pi cancels on that integration class. With me? Now, you can divide by rho, and if you do that, this becomes squared. So you find that d rho here is equal to k, for this problem that I created, rho squared, right? And then it would be divided by 3. And this is good for rho greater than 0, less than a. Agreed, everyone? Now I have to go for rho greater than a. I'm going to flip the page, if you don't mind. Okay. Now for rho greater than a, now I'm outside the region where the charge density exists. Correct, class? And I write it down again. I'm going to have the integral of d dot ds over the closed surface. Closed surface is equal to the integral of, in this case, it would be rho v dv over the volume. And this is just, this means a closed surface. But I already know what this is, don't I? The integral of d dot ds is going to be the same always, right? And I made my height 1 on purpose. So this integration, just as before, becomes simply 2 pi rho times d rho. You all with me on this, class? Right? Now this integration, I have to evaluate. But I got a hard limit. It's a triple integral, right? I put the charge density first, that's k times rho. And then I put the differential unit of volume in cylindrical coordinates. The differential unit of volume is going to be rho d phi, d rho dz. Agreed? All right. Here, phi goes from where to where? Thank you. 0 to 2 pi. Some people do not like to be called on, but I try to get participation. It will help everyone. Now, what about rho? Fowler for the last time. Where does rho go from?
Could you do rho from 0 to rho again?
We're at a distance greater than A. All right, it goes from 0 to A, remember? Because there's no charge density beyond this. It goes, here's the 0 to A deal, all right? Remember, you can only go, that's where the charge density exists. If we went beyond A, then we'd have to put a 0 here, wouldn't we? The charge density would go to 0. Follow me? And 0 integrated over anything is still 0. So that's the reason. You guys look at this. I'm going to keep bugging you guys. I'm not trying to irritate you, but I'm trying to make my point. What about Z?
0 to 1.
I can't hear you. What? Whoever say it again.
0 to 1.
0 to 1, exactly. And that's nice because if you look at the DZ integration at Z from 0 to 1, we don't even need it, do we? It's gone, correct, class? Now, here we have the next one is the rho integration. Well, we have K rho squared. When we integrate that, we would get K rho cubed over 3, right? Or I'm sorry, yeah, K rho cubed over 3. Evaluated from 0 to A would be K times, it would be A cubed over 3, right? Now we go to A, correct, class? And then finally, the phi integration, d phi integrated is phi from 0 to 2 pi is 2 pi, right? So that is the amount of charge inside. Agreed, everyone? And that has to be equal to the integral of d dot ds, which is 2 pi rho d rho. And you can look at this with me. First thing you notice is the 2 pi's cancel, correct? And then when we divide by rho here, you can see that d rho has this form when we're at rho greater than A, correct? Now, one thing you notice about that is it varies as 1 over rho, doesn't it, class? It varies as 1 over rho. Remember what a line charge, if you have a line charge that's infinite, how the electric field varies. It's 1 over rho, it's right. It's rho L over 2 pi epsilon naught, right? And you can see that the behavior is true for both the sphere and the line, infinite line charge. Once you get beyond where the charge exists, it starts behaving like either a point charge or like a line charge, all right? It will vary in the same way. So that's my spiel on Gauss's law. I'm going to give you some problems. I'm going to tell you one last thing before you go. And realize delivering this information through these lectures is awkward for both you and me. You're probably uncomfortable talking and Zooming and trying to absorb everything I'm saying. I provided you with a little PowerPoint to view and use, if you will. But this is something this is where I had my last point in the lecture. That is the integral form of Gauss's law. Now, in most physical laws, there is an integral form and there's a differential form. And the differential form is this: the divergence of D is equal to the volume charge density. Now, if you have your book, y'all have your book? Get your book and look at the last page in the book. And you'll see something called divergence. Y'all see that? Get your books and flip there. Now, this is the divergence operator in all 3 coordinate systems. A divergence operator is like a derivative, only it's a directional derivative. But in this case, it has no direction. It's a scalar term. And it takes the derivative, for instance, if we were in Cartesian coordinates, derivative of the vector component in the x direction with respect to x, plus the derivative of the vector component in the y direction with respect to y, plus the vector derivative, the derivative of the vector component in the z direction with respect to z. And we'll take that next time. I'm going to give you a few problems about that, but I think because it's just turning the crank on an equation, it's fairly easy to see. Do y'all see this? This is a simple derivative operation. If I ask you for the divergence of a vector, it's a simple derivative. Okay? Any questions before we go? or any information for the good of the group?
Do we have quiz on this Friday?
No. No. And you know, this stuff is, I have to adapt as we go. I can't tell you how fast we're going to cover certain pieces of material because it's Zoom, and frankly, some points just take longer to get across. I'm not going to be one of these guys that gives you a Panopto video to watch and not answer questions or interact. It's, to me, it's really, that's a discredit to students, because if you're going to get anything out of this course, I mean, the way to maximize the amount you get out is interact. Ask questions. Don't be shy. I'll call on everybody and irritate a few people, but it'll keep this conversation going, and you'll start really learning this stuff, hopefully. Now, I'll tell you one thing. Electromagnetics is probably one of the more difficult courses in EE. I mean, it's dependent on who you get. In my course, I'm usually either loved or hated. There's no gray area, because some people get this stuff and others, no matter what they do, don't. And it's just something about being able to visualize these problems. But I'll do my best to convey this information. And if you have any suggestions for me, please do it. Now, you all hear any other information going on? Either students that you can help me pass on to me? Nothing? You know about the bars, right? There was another one that they found. They did contact tracing, and I forgot the name of it. It's downtown. Do you know? It's not the Draft House, and it's not Sky Bar. It's something else. But if piece of advice: stay out of the bars, stay out of restaurants. Go outside and do whatever you would do outside by the, like the Ag Heritage Red Barn or something like that. You'll be safe. Nothing else, guys? Okay. I'm going to give you some homework. Please do it by Friday.